We're now going to take a look at a form of convective heat transfer whereby the fluid adjacent to our surface is going through a phase change. And so that could be going from a liquid to a vapor, in which case we would call it boiling, or we could be going from a vapor back to a liquid, in which case we would call it condensation. We're going to begin in the next couple of lectures here looking at boiling heat transfer. And what we're going to find is that the values of the convective heat transfer coefficients for phase changes are very, very large because there's a lot of energy associated with that. But this is a very important area industrially because we have many, many systems, be it refrigerators or Rankine power cycles, where we have vapor power cycles or vapor refrigeration cycles where we go through a phase change from liquid to vapor and then vapor back to a liquid. So very important for engineering. And so what we're going to do, we're going to look at the boiling processes in this lecture and the next one. So to begin with, what is boiling? Well, boiling, we know it's when we're going from a liquid to a vapor, but there are certain conditions that must be met. And so let me just break those out and then we'll discuss them. Okay, so there is the description of boiling, and what is happening with boiling is we have a solid-liquid interface, and the solid, so the wall temperature, the surface temperature, needs to exceed the saturation temperature of the liquid at the liquid pressure. So if you recall from thermodynamics, we use steam tables in order to determine what the saturation temperature would be for a given pressure. And that's what we'll be doing again in heat transfer. We'll be looking at steam tables in order to pull out properties, and we'll be looking at the heat of vaporization, that is going through the phase change from a liquid to a vapor. So boiling, we're going from a liquid to a vapor. And when we look at boiling heat transfer, I mentioned that the convective heat transfer values are very, very large, and we'll see that both for boiling and condensation. But to describe, we just use Newton's law of cooling like we've done before. Now, for our delta T, we're going to have our surface temperature, our wall temperature, and the other temperature is going to be the saturation temperature. So typically, it will make sense. You have to have the wall higher at a higher temperature than the saturation temperature in order to have boiling take place. And so that is the delta T that we will use. And given that we see this so many times, we give this a name. So we label this TW minus Tsat as being the excess temperature. So if you're looking at plots in a book on boiling heat transfer, sometimes you'll see delta Tx, sometimes you'll see delta Te, E denoting excess, and what that is showing is T wall minus T sat, or that could be T surface minus T sat, depending upon the book that you're using. So what are we looking for here? Well, as with all of the other things that we've been doing, when we've looked at convective heat transfer, we want to know how to estimate H. So what we are after, or what we are interested in, is estimating H. But before we jump into the correlations that are used for boiling heat transfer, what I want to do is begin by looking at the physics of what is going on through the boiling process. And what we're going to do, we're going to begin with an experiment that everybody studying heat transfer should do, and that is to take a pot of water, put it on top of the stove, and watch the water boil. And this is something that I did years ago when I took heat transfer, and that's what we're going to do right now. We get to repeat the experiment. So what we have here is a video, and it's going to get a little loud because boiling is not a quiet process, but and I've sped it up. Don't worry, we're not going to be waiting 15 minutes for water to boil. It's going to go a little quicker. But there you can see a pot. We have the infrared camera on the lower left, and all of a sudden you can see natural convection cells starting to form there. on the IR camera. And then if you look from the side view, you can see the index of refraction variations. You have natural convection going on. What I'm doing every minute, I pull out about 5 seconds of video here. And so we're watching time evolve relatively quickly. There you can see the natural convection more evident in the pot. We have more mixing on the IR camera because it's a more uniform temperature. And there are little bubbles that are coming up, but we're not boiling yet. So those could just be air bubbles that are attached to the surface. But that will become important as we watch the process. So let's continue observing what's going on. And then we have the top view camera in the upper left where we can see from the top. There's a little bit of steam coming out there. But as we move on, noise is going to start. So we start getting noise coming in here. And what that noise is caused by are bubbles forming at nucleation sites on the surface, and then they collapse. And it's that collapsing process that we hear. And now we're going to go to high-speed video. And so what we can see are bubbles that are forming on the surface, and they're trying to move up, but the fluid is at a cooler temperature, and the bubble through heat transfer collapses. It doesn't have enough energy to make it to the top. And then some bubbles get a little further, so this is a little later in time. And you can see some bubbles ascending a little higher, but still they're collapsing. The pool temperature is not hot enough in order to sustain the bubbles going to the surface. And as we go on in time, we're going to start to see here the bubbles are starting to make it to the surface. And so there you can see the odd bubble making it to the surface. And as we wait a little bit longer, we get more boiling occurring. And there we have more and more bubbles. You see the surface is moving around quite a bit. And then finally we're going to have full saturated pool boiling coming here. And there you can see all the bubbles making it to the surface, vapor coming out. And so that would be full boiling taking place, saturated pool boiling. Prior to that it was subcooled because we weren't at a high enough temperature. And there you can see the IR camera. As the bubbles come to the surface, we get pockets of very hot fluid, and that's the more yellow temperature in the red mix that we're looking at. And so that is a video describing boiling. And so you might want to do that if you have some time, go and put a pot on the stove top and watch the bubbles form and then watch the boiling take place, because that will help you as we go on into the next segments here throughout this lecture, looking at the different processes that occur within boiling heat transfer. But what we saw in the video there, at the beginning we saw subcooled pool boiling. And this was where we had bubbles that were forming, but then they would shrink and they would, after a while, they would collapse. So this is our free surface up here. And so that was subcooled pool boiling because temperature of the liquid is less than the saturation temperature. And so the bubbles lose energy as they move up. The other thing that we saw later on, we saw saturated pool boiling. And here again, this is our stovetop, our solid surface. And we have our liquid. Now in this case, what was happening is the bubbles were forming and they were able to make it to the surface. And then we had the vapor coming out of the surface. And this was where T liquid was approximately equal to the saturation temperature at the atmospheric pressure. This experiment was conducted at an atmospheric pressure around 89 kPa, but that's not a big deal. It doesn't really matter. You get the same sort of effects in terms of the visualization of it. So that is the difference between subcooled pool boiling, which is what we saw earlier, and then saturated pool boiling. But we'll look at this in more detail in the next couple of segments as we study the aspects of boiling and boiling heat transfer.